Hello, everyone. Thanks for taking time to watch my talk. Today, I'm going to talk about heavy traffic analysis of queuing systems when there is no complete resource pooling. I'm going to explain what this means as we go along. This is a joint work with my PhD student, Daniela Hurtado-Lange. And for those of you that are looking to hire, Daniela is going to be in the job market this year. So we see stochastic processing networks all over the place. What are stochastic processing networks? They're basically a bunch of customers that arrive into the system, they're a bunch of servers, and the customers need service, and they have to wait if the servers are all busy, and after that they leave the system. And such systems are very, very general. They appear all over the place. For example, transportation systems, toll booths, call centers, ride-hailing systems, meal delivery platforms, cloud computing systems, wired networks, wireless networks, and so on. And the main goal in many of these systems is to minimize delay. Actually, there are two goals. The first goal is to maximize throughput of the system, and a second or more harder to achieve goal is to minimize delay. And to model these systems, these are a wide variety of systems. And to model these, there are many different models, which are all called as stochastic processing networks. The simplest model is when there is a single server and there's a single queue, and customers come and join this queue, and the server works to serve them. And then after they finish their service, they leave the system. This is like a MM1 queue or GG1 queue or whatever. A more intricate system is like a bank queue or the queue at an airport where there are a bunch of servers, multiple servers, and there's a single queue. Or sometimes there may be multiple servers and then separate queues for each of them. And then maybe customers join each, customers arrive into each of these queues separately, but possibly the correlations between the arrivals of the customers and correlations between the servers as well. Or there could be a single queue, a single stream of customers coming in. And then even though there are multiple queues on multiple servers, the customers have to go and pick one of those queues. This is what happens in a supermarket checkout system. And many a time there could be separate queues and separate servers, but there are constraints between these servers. Only a subset of queues can be active at each time, and then one has to use a policy to serve them. Or in the most general setting, there are a bunch of queues and servers, and then after customers finish service in one of the queues, they actually go and join a different queue. This is called a network. So what we want to do is we want to come up with a single model that encompasses all of these, and then we want to analyze it and give delay bounds for that work for all these systems. And that's what we're going to do today. And when I say all, precisely speaking, I'm only going to consider the left 4 systems and many more systems than just these, as I'm going to explain. The load balancing system, the supermarket checkout system, can also be analyzed using the same framework, but there's a small difference, and that's why we don't talk about it today. But the network system that's at the bottom right of the screen, that's much harder to analyze, and then we're not going to consider that. So this is the outline of today's talk. I'm going to present a very, very general model called generalized switch, which encompasses all the systems that I talked about. I'm going to talk about the capacity region of the system. Then I'm going to explain something called heavy traffic regime. I'm going to explain why we need it. And in the heavy traffic asymptotic, I'll present our result on the mean steady state queue length. And our result is going to be, since it's very general, it's going to look quite complicated. I'm going to present several special cases which are going to be useful. And if time permits, I'm going to very briefly talk about the proof sketch and eventually conclude. So let's start. So first, I want to start with a very specific model called the input queued switch model. In an input queued switch, there are L square queues in all. One can think of them as being arranged as in a matrix, an L cross L matrix, where the rows correspond to inputs, the columns correspond to outputs, and there are L inputs and L outputs. And there is one queue corresponding to each input-output pair. And arrivals of jobs or packets or customers come into each of these queue according to an arrival process. And this arrival process is assumed to be IID across time, but across the queues will allow will not assume independence, will allow dependence across the queues. And for each queue, the arrival process. So this is a discrete time system. So in this whole talk, I'm talking about discrete time systems. So the number of arrivals in each time is IID, and that has mean lambda and variance sigma square. And there are also correlations which I'm not introducing here. And the main challenge is that not all these queues can be active at the same time. So there are constraints in the system because of which at most one queue can be active in each time slot, in each row, and at most one queue can be active in each column. And whenever a queue is selected to be active, we can serve exactly one packet from the queue, if there is a packet. If the queue is empty, then we waste that service. And so the problem is to pick which set of queues will activate in each time. And this is equivalent to saying that I want to pick a schedule at each time, and my schedule should form a permutation matrix. I could have explained the same thing using bipartite graphs, in which case the schedule should form a perfect matching. And why is this problem interesting? There are multiple reasons. One of the reasons is that this can be thought of as a model, an approximation for a data center network. So all of us use mobile phones, smartphones, and there are many apps on these phones which are powered by cloud computing. And cloud computing is mostly powered by data centers which have like hundreds of thousands of servers. And these servers want to talk to each other. So there's a network that enables this connectivity. And then in this network, we want to figure out how to schedule the movement of packets. And that can be modeled by a huge input queued switch that's of this form. And whenever we look at a queuing system, a stochastic processing network of this form, the first question we are interested in is what is the capacity region of the system? And capacity region means that if you're outside this region, the system is going to become unstable. The queue length will go to infinity. If you're inside this region, there's some algorithm. If you're smart enough, you can stabilize the system. And finding such an algorithm is itself a challenging problem, which we'll get to in a bit. So for the switch, the capacity region has a simple form. All it says is that the total arrival rate in each row is less than or equal to 1, is at most 1, and the total arrival rate for each column is also at most 1. And this is fairly intuitive because in each time slot, in each row and column, we're serving at most one packet. So that's what the capacity region is saying. Or there's another way of thinking about it, which is that the set of all valid schedules, valid set of queues that can be active, is the set of all permutations. So the capacity region is actually simply the convex hull of all the permutations. And the second form is going to be useful as we go along. So input queued switch is one specific model, but I said that I want to study a very general class of stochastic processing networks. And what we'll study is what is called as a generalized switch model. And this is very similar to switch, but I'm going to generalize it in two specific ways. And so I again have a bunch of queues. They have arrivals, IID across time, discrete time system, and there could be correlations across the queues in terms of the arrivals. And now when I talk about the service, remember in a switch, you can serve at most one queue in each row and each column. Here, what I do is I allow for any general set of constraints. So I don't care. I can think of it as a graph. So based on your system, maybe you have a wireless system, and then there are some specific constraints. I can encode them into a graph, and then at the end of the day, I can have any general constraints. I can say that these two queues cannot be active at the same time, but the first one and third one can be active, and so on. I can give any complicated set of constraints. That's the first generalization. I don't have to worry about this matrix or bipartite graph structure. The second generalization is the following. Remember, in an input queued switch, whenever I activate a queue, whenever I'm serving a queue, I can serve exactly one packet, one customer in each time slot. So I can generalize that. And I can say that the number of customers I serve can be random. It depends on the schedule. Actually, I can make it further, even more general. And then I can say that there is something called channel state. So there is some amount of randomness inherent in the system, which I capture by what is called as channel state. And my interference constraints can change based on the state. So at every time, nature picks the state in an IID manner across time. And then once I know which state I am in, I have a specific set of constraints. If I'm in state 1, I have one set of interference constraints. If I'm in state 2, I have a different set of interference constraints which determine which subset of queues I can serve, and so on. And the question is how to pick the scheduling problem is to pick the service vectors. So let me give you several examples that fall into that can be modeled using this general model. So obviously the input queued switch is a special case. I can think of ad hoc wireless network as another case. For input queued switch as well as ad hoc wireless network, the channel state is fixed. What this means is that in an ad hoc wireless network, so each server is like a mobile phone, and if I'm trying to use my mobile phone, then someone who is very close to me cannot use the same wireless channel. So if I'm active, my neighbors cannot be active. And when I'm active, the service I get is determined. I can think of a more general setting where, because of the underlying randomness in the wireless channel, the service that I get changes with time. Then I can think of it as the channel state. The channel state is determined by nature, and the service I get is random depending on that. And another system is a parallel server system where there is an inherent randomness in the service process, and I can again capture that. I can model it using the channel state. Okay, and what is the capacity region in this more general, more complicated system? It has the following simple form. So suppose there is a single channel state, then I can simply take the set of all allowed schedules, and I can take convex hull of them, and that gives me my capacity region. Now, since I have multiple channel states, I simply take a convex combination of the convex hulls, and that gives me my capacity region. And I can represent this capacity region in terms of a polytope. So we're going to work with this polytope as we go along. And then how do we do scheduling? In this talk, we focus on what is called the MaxWeight matching. And what MaxWeight matching does is the following. First, we find out what channel state we are in. Once we know the channel state, we know what set of schedules are allowed. And among all these schedules, I find the schedule that has the maximum weight using Q length as weight for each queue. And this is called the MaxWeight algorithm. And the queues evolve as follows. My Q length in the next time is the current queue length plus arrival minus service. And if I don't have enough packets to serve, then there'll be unused service. So let me now state the main result. So ideally, I mentioned how I want to understand delay in these systems, or understanding delay is same as understanding queue lengths. But in these kind of systems, exactly characterizing queue lengths is very hard. So what we do is we look at the system at some asymptotic regime. The regime we are focusing on is called heavy traffic regime. In this regime, what we do is we let the arrival rate be very, very close to the maximum capacity in the system, and then see what happens in this asymptotic regime. So for example, if you have a single server queue, the arrival rate lambda should be less than mu, that is the capacity region. So in heavy traffic limit, I let lambda approach mu. More generally, for the generalized switch, I have the capacity region, which is a polytope, and I pick one point on the boundary of this polytope, we'll call it nu, and then I'll make my arrival rate approach this point on the boundary as in the asymptotic limit, and then see what happens. So why do we study heavy traffic regime? The main reason is because of something called state space collapse. So again, I have this point on the boundary, and my arrival rate is approaching this point. So it can be shown that the Q length vector, it's a vector in this n-dimensional space. I have n queues, so Q length vector is a vector in this n-dimensional space. Suppose my limiting arrival rate is in the interior of a facet. Then it is known that the Q length vector behaves as if it just lies on this line. So this is called a state space collapse. And when the limiting arrival vector is in the interior of a facet, we say that complete resource pooling is satisfied. Because we'll see that in this case, the system behaves as if it's a single server queue, and that's why we call it complete resource pooling. But if this arrival rate is not in the interior of a facet, but it's at the intersection of multiple facets, so it's in the interior of a lower dimensional phase, then we'll see that the Q length vector again has a collapse, but now it's not one-dimensional, it's multi-dimensional. It collapses into the normal cone, into the cone spanned by the normal vectors of these facets. at whose intersection the limiting arrival vector is. And so why do we care about state space collapse? So in the complete resource pooling case, when the collapse is into a single dimensional subspace onto a line, the whole system with n separate queues behaves as if it's like a single server queue. And a single server queue is very easy to analyze. So there is a lot of work in literature on studying systems that satisfy this complete resource pooling. And the heavy traffic behavior is pretty much like a single server queue. But when complete resource pooling is not satisfied, we still have state space collapse. But the collapse is onto a lower dimensional space, which is not a one-dimensional subspace. It's not a line. So I have capital N number of queues, and if my state space collapse happens to a subspace of dimensionality little n, then it behaves as if there are n separate queues in the limit. And this is what we want to analyze, and there is very little work in literature on these kind of systems. Pretty much the only thing that is known is in the case of input queued switches and what is called as bandwidth sharing networks. So now I'll directly get into our main result. So this is my generalized switch. The capacity region has some form of in the form of some polytope, and since it's a polytope, I can represent it as inequalities of this form. I'll come to it in a minute. So my theorem looks like this. Let me parse this for you. So in the left-hand side, firstly in the heavy traffic limit, the Q lengths go to infinity. They go to infinity as the heavy traffic parameter epsilon goes to 0. Remember, epsilon somehow captures how far you are from the capacity region. So what we want to do is we want to find out the rate at which it goes to infinity. So we multiply by epsilon and then take the limit. And we have a first moment on the Q lengths. Q lengths are given by a vector. So we have bound on a certain linear combination of the Q lengths, where this linear combination comes from the limiting arrival rate that that we are approaching on the boundary. So that's the left-hand side. On the right-hand side, there are two terms. The first term depends on the main thing you should notice is there is the sigma A here and sigma CS. So the sigma A is the covariance matrix of the arrival process. So the first term depends on the arrival process, and the second term depends on the service process. So the sigma CS stands for the channel state. Sigma CS captures the covariance of this channel state process. And the main thing to notice is that in heavy traffic limit, it is well known that the answer depends only on the second moments. It doesn't depend on the higher moments of the arrival or the service. That's why we only have these covariance matrices showing up here. And so both these terms are certain linear combinations of these covariance matrices. And these depend on the C matrix and H matrix. What is C? So when I'm approaching a point on the boundary of the capacity region, I look at the hyperplanes that determine that facet or multiple facets, and the C vectors are the normal vectors of those hyperplanes, and capital C matrix is a matrix whose column vectors come from these normal vectors. And what is H matrix? H matrix is simply the projection matrix onto the state space collapse region. So this completely characterizes the heavy traffic behavior of a generalized switch. To understand this better, let's see multiple examples. So first, let's think of a input queued switch. So there's the same input queued switch I showed you before. And then if I look at the sum of all the Q lengths, which is what I'm interested in to get the mean delay, then here the multiple terms. The first term is simply depend on the variance of each arrivals into each queue. The remaining terms depend on the covariance between the queues. And in particular, I care about covariance. If I'm looking at this queue, I care about the covariance with respect to the other queues in the row, covariance with respect to the other queues in the column, and covariance with respect to everybody else. Those are all these covariance terms. In particular, if I have IID arrivals, if my covariances are all 0, this reduces to this nice simple form, which was obtained in previous work. So what we do is we basically generalize the previous work to allow for dependence across the queues. And this is very important in real world data centers because the IID, if the arrivals are IID across queue, that is very unrealistic assumptions, because in real data centers, people have measured and they notice that the arrivals are very highly correlated. So a second example I want to talk about is I have a bunch of servers and a separate queue. The arrival process are all different. But the thing is, the arrival process can be correlated. Service process is also correlated. And the service can also be random. If I have a single queue of this form, it reduces to what is called as the Kingman bound. When I have multiple independent queues, that's very simple. It's just apply Kingman bound to each of the queues separately. And what I'm doing here is it's more general than that because all these queues are correlated. And what we show is that the sum of the queue lengths in heavy traffic, weighted sum, weighted by mu's, depends only on the variances. The covariance terms don't appear, which is very surprising. If these were independent, one would expect this answer from Kingman's bound. But even if the arrivals and services are not independent, it turns out that the answer depends only on the variances and not covariances. And turns out this is true not only for a parallel server system, it's true for any general system. If I have a generalized switch where I'm approaching a point which is actually a zero-dimensional phase, which means it's actually a corner point of the capacity region. Then my state space collapse happens into the full dimensional space. And it turns out that in this case, the covariance of the arrivals don't matter. It only depends on the variances. So, parallel server system is a special case of such a system. So I'll stop here because I'm running out of time. I'm going to skip the remaining slides, which are mostly on the proof technique. So hopefully I illustrated how the generalized switch model is a good model for a very, very general stochastic process network. And we studied the heavy traffic behavior in a generalized switch. So thank you. Thanks for taking time to attend my talk.